There is a farmhouse in Devon, England, that has been continuously occupied since 1540. Not maintained, not restored. Continuously occupied and continuously standing for nearly 500 years. The walls are approximately 2 feet thick. They are made of subsoil, straw and water. No fired brick, no concrete block, no synthetic insulation product of any kind. The interior of that house stays between 60 and 72 degrees Fahrenheit through most of the year, without mechanical heating or cooling. In summer, the walls absorb the heat of the day and release it slowly through the night, keeping the interior cool during peak hours. In winter, the walls store what heat is generated inside from a fire, from cooking, from body heat, and release it back into the space slowly over hours, so that a fire lit in the morning still contributes to warmth by evening. The material that makes this possible is called cob. It is a mixture of subsoil clay, coarse sand and straw fiber, mixed together with water, formed into a monolithic wall mass and allowed to dry. The raw materials cost nothing or nearly nothing if you have access to ground. The labor is unskilled. The technique requires no tools beyond your feet and your hands. It has been used continuously in human construction for at least 10,000 years on every inhabited continent. The thermal performance of a correctly built cob wall exceeds the thermal performance of a standard hollow concrete block wall of equivalent thickness by a measurable margin. Not in every metric, but in the metric that actually determines how comfortable your house is to live in and how much energy it takes to keep it that way, cob wins. And it costs, in raw materials, approximately what the ground beneath your feet is worth. I want to explain to you why that is true, what the science behind it is, how people have been using it for 10 millennia, and exactly what you can do with this knowledge this weekend, on a wall that already exists or on a structure you are planning to build. Because the reason cob disappeared from mainstream construction guidance has nothing to do with performance, and everything to do with the fact that you cannot sell a patent on subsoil. Part 1. What cob actually is and why it works. The word cob comes from an Old English root meaning a rounded lump or mass. It refers to the technique of building walls by stacking and compressing handfuls of the mixed material, wet clay soil, sharp sand and straw, directly, without formwork, without bricks, without mortar joints. The wall is monolithic. There are no joints to fail, no planes of weakness between courses, no cavities for water to enter and freeze. The three ingredients work together in a way that is more sophisticated than it appears. Clay is the binder. When wet, clay particles, which are plate-shaped at the microscopic level, slide over each other, making the mixture plastic and workable. As the clay dries, those plates pack together and form a rigid matrix through surface tension and electrostatic attraction. The dry clay matrix is hard, dimensionally stable, and has significant compressive strength, typically between 300 and 600 pounds per square inch in a well-mixed cob, which exceeds the compressive strength requirements for a load-bearing wall in most residential building codes. Sand is the structural aggregate. Clay alone shrinks when it dries, because the water leaving the matrix causes the clay plates to contract. Without aggregate to maintain the volume of the material during drying, a pure clay wall would crack severely. Sharp sand, not rounded beach sand, but angular quarry sand or sharp river sand, interlocks mechanically within the clay matrix and resists shrinkage. The ratio of clay to sand is the critical variable in cob mixing, and getting it right is the foundational skill of the craft. Too much clay and the wall cracks. Too much sand and it crumbles. Straw is the tensile reinforcement. Compressive materials fail in tension. That is, they crack when pulled apart, rather than when compressed. Clay and sand together have good compressive strength, but limited tensile strength. Long straw fibers distributed through the mix act as a three-dimensional fiber reinforcement network, the same role that steel rebar plays in concrete, or that horsehair played in traditional lime plaster. The straw fibers bridge incipient cracks, distributing stress through the wall mass, instead of allowing it to concentrate at a single point. A well-built cob wall that incorporates long, intact straw fibers does not crack in the way that concrete or unreinforced masonry cracks. It is tough as well as hard. The thermal performance of cob is a function of its density and its specific heat capacity, two material properties that determine what physicists call thermal mass. Cob has a density of approximately 100 to 120 pounds per cubic foot and a specific heat capacity of approximately 0.2 British thermal units per pound per degree Fahrenheit. These numbers combine to give cob a volumetric heat capacity of roughly 20 to 24 British thermal units per cubic foot per degree Fahrenheit. For comparison, hollow concrete block, the standard construction material for residential exterior walls in many parts of the world, has a volumetric heat capacity of approximately 10 to 12 British thermal units per cubic foot per degree Fahrenheit. This means that cob stores roughly twice as much heat energy per unit volume as hollow concrete block. That is, the R-value conversation people get confused about. If you measure cob by steady-state R-value per inch, the metric used to rate fiberglass bats and foam board, it performs modestly, around R0.4 to R0.5 per inch. A hollow block wall performs similarly. Fiber insulation performs far better on this metric. But steady-state R-value measures resistance to heat flow under constant conditions. Real climates are not constant. They cycle. The outdoor temperature goes up during the day and down at night. The indoor temperature rises when the stove is lit and drops when it goes cold. The metric that captures how a wall actually performs in a cycling thermal environment is called thermal lag and thermal damping. And on these metrics, a thick cob wall is dramatically superior to a thin, high R-value insulated wall. A 2-foot cob wall has a thermal lag of approximately 8 to 12 hours. Heat hitting the exterior surface at noon arrives at the interior surface around midnight, when the outdoor temperature has already dropped. The wall is absorbing heat when it is unwanted outside and releasing it when it is needed inside. That is passive climate control. It requires no equipment, no energy, and no maintenance. Part 2. 10,000 years of documented use. The oldest known cob structures on Earth date to approximately 8000 BCE, in the region that is now Turkey and the Levant. The Neolithic settlement at Ain Ghazal in present-day Jordan, one of the largest early human settlements ever excavated, shows cob wall construction in structures dated between 7250 and 5000 BCE. These are not primitive shelters. Ain Ghazal was a town of several thousand people. The walls that have been partially preserved after 9,000 years of burial show the characteristic monolithic structure, fiber reinforcement, and dense clay matrix of correctly built cob. In England, the tradition of cob building was continuous from the Neolithic period through the 20th century, with the peak of cob construction occurring between roughly 1500 and 1850. Devon and Cornwall in southwest England have the highest surviving density of historic cob buildings anywhere in the world, an estimated 20,000 cob structures still standing, many of them in continuous residential use, the oldest dating to the medieval period. The Devon Earth Building Association has documented and studied these structures in detail, and their findings are consistent. Properly built and maintained cob walls last indefinitely. The maintenance requirement is simple. Keep the base dry and keep the top covered. A cob wall with a good roof overhand and a stone foundation course above the splash zone will not deteriorate. In Yemen, the old city of Shibam, sometimes called the Manhattan of the desert, contains multi-story cob and mudbrick towers that have been continuously inhabited for over 500 years. The tallest reach 9 stories. They are built from the same basic material, local subsoil, straw, and water. The towers have survived desert heat, seasonal rain, and the mechanical stresses of earthquake activity in the region. They are a UNESCO World Heritage Site, not because they are curiosities, but because they represent a continuous living tradition of earthen construction that functions at a scale most people in the modern world would not believe possible from these materials. In the American Southwest, the Pueblo structures at Taos, New Mexico, have been continuously occupied for over 1,000 years. The walls are adobe, a close relative of cob, differing primarily in that adobe is formed into dried bricks before assembly, while cob is placed wet and monolithic. The thermal mass principle is identical. The Taos Pueblo receives over 300 days of sunshine per year, with summer temperatures exceeding 90 degrees Fahrenheit and winter nights dropping well below freezing. The thick earthen walls moderate these extremes so effectively that the interior remains habitable throughout the year without mechanical conditioning systems. In West Africa, the Great Mosque of Djenné in Mali, the largest mudbrick building in the world, has stood since the 13th century, rebuilt to its current form in 1907 on the original foundation. The walls are up to 24 inches thick. The building shelters thousands of worshippers from temperatures that regularly exceed 100 degrees Fahrenheit on the exterior. The interior remains 15 to 20 degrees cooler than the outdoor air at peak heat, purely through the thermal mass of the earthen walls. The annual maintenance ritual décrépissage, in which the entire community replasters the exterior together, is a social institution. The building requires maintenance. It does not require replacement. The documentary record of COP's performance across climates and centuries is not ambiguous. This is a material that has been field-tested at scale across hot deserts, cold winters, wet temperate coasts, and dry continental interiors for longer than any synthetic building product has existed. The results are visible in standing structures on 6 continents. Part 3. The humidity regulation mechanism. There is a second thermal and comfort benefit of COP that is less widely understood than thermal mass, and in some ways more practically significant for residential use. COP walls regulate interior humidity passively and automatically. Clay is hygroscopic. It absorbs moisture from air that is relatively humid and releases moisture into air that is relatively dry. This property is the same property that causes clay-rich soil to swell when wet and shrink when dry, makes a clay wall surface act as a passive humidity buffer for the interior space it encloses. The mechanism works as follows. When indoor activities, cooking, bathing, breathing, washing, raise the relative humidity of the interior air, the clay surface of the wall begins to absorb water vapor from the air into the outer layer of the wall mass. This process continues until equilibrium is reached, or until the humidity source is removed, at which point the wall gradually releases the stored moisture back into the air. The wall is not a perfect humidity controller. It does not hold the interior at a fixed relative humidity the way a mechanical HVAC system can, but it moderates peaks and troughs in humidity in a way that significantly improves the comfort and air quality of the interior space. The Building Research Establishment in the United Kingdom conducted a series of studies in the 1990s and early 2000s comparing the hygrothermal performance of earthen wall construction with conventional masonry and timber frame construction. Their findings confirmed that earthen-walled rooms showed measurably lower peak humidity during high moisture events and higher minimum humidity during dry periods, compared to equivalent rooms with sealed synthetic wall surfaces. The practical result is that condensation forms less readily on cold surfaces, mold growth conditions are reduced, and the air feels less stuffy in summer and less dry and brittle in winter. This is relevant to the modern construction context in a way that is rarely discussed. Contemporary building practice, particularly in the United States, treats vapor control as an engineering problem to be solved by vapor barriers polyethylene film applied to the interior face of insulated stud walls to prevent moisture-laden interior air from reaching the cold exterior sheathing where it could condense. The vapor barrier strategy works when installed perfectly. In real-world construction, where polyfilm is penetrated by fasteners, torn around electrical boxes, and imperfectly lapped at seams, it creates exactly the conditions it is intended to prevent. Moisture trapped inside a wall cavity with nowhere to go, feeding mold growth in insulation bads and wood framing that may not become visible for years. A cob wall has no cavity, no insulation bads, no framing lumber, and no vapor barrier. Moisture that enters the wall from either side migrates through the clay matrix and exits when conditions allow. The wall breathes. It cannot trap moisture in a way that causes concealed decay because there is no cavity to trap it in. The entire wall mass is the moisture management system, and it is self-correcting. Part 4. Why it disappeared from mainstream construction. COP did not disappear because it stopped working. It disappeared because it was incompatible with the economic and organizational structure of modern industrial construction. The shift began in earnest in the second half of the 19th century when two developments coincided. First, fight brick became dramatically cheaper due to industrialized brick production, mechanized clay processing, continuous fire kilns, and rail transport of materials. Fired brick could be produced at a central factory, shipped anywhere, and assembled by workers with minimal training following a standard specification. It was a product. Cob was not a product. Cob was a process, and the quality of the result depended on local soil conditions, local knowledge, and skill judgment about mix ratios and wall formation. That was not easily reduced to a written specification. Second, the emerging profession of architecture and the codification of building regulations in the late 19th and early 20th centuries systematically favored materials that could be specified precisely, tested under laboratory conditions, and assigned consistent performance values. Fired brick has a compressive strength that can be measured and certified. A concrete block has an R value printed on a datasheet. Fiberglass insulation has an R value per inch that is standardized by ASTM testing protocols. Cob, whose performance varies with the clay content of the local soil, the length and quantity of straw fiber, the degree of compaction, and the drying conditions, could not be reduced to a single number. And building codes require numbers. This is not a conspiracy against earthen construction. It is the predictable result of applying industrial quality control logic to a material that is inherently local and variable. The logic was sound for its purpose. The side effect was that an entire category of building material, one that had served human construction for 10,000 years with documented success, was made effectively unspecifiable under modern building codes, and therefore unbuildable under modern permitting systems, and therefore invisible to the modern homeowner, who relies on permitted construction for everything they build. The post-World War II housing boom in the United States and Western Europe accelerated the consolidation around a small number of standardized construction systems: wood stud frame, concrete masonry unit, poured concrete, that could be built quickly by large crews, financed through standard mortgage products and insured under standard policies. Cob fit none of these criteria. It was slow to build. It required no purchase materials in its basic form. It could not be easily financed as a commodity in a construction loan. And it was not covered by standard homeowners insurance, because no actuarial table existed for its failure modes. The result, within 2 generations, was that practical knowledge of Cob construction essentially vanished from the mainstream building trades in North America and most of Western Europe. It survived in academic architecture programs, in rural vernacular traditions in Devon and Yemen and West Africa, and in the early natural building revival movement of the 1970s and 1980s that produced the foundational modern technical literature on the subject. But for a homeowner in the United States in 1980 who wanted to build with Cob, there was no contractor to call, no permit precedent to cite, and no material supplier to source from. The knowledge existed. The institutional pathway to use it did not. Part 5. What you can actually do with this today. The natural building revival of the last 30 years has produced a substantial body of tested, practical knowledge about modern Cob construction. There are now building code provisions for earthen construction in several U.S. states, most notably New Mexico and California, which have adopted ASTME 2392 as a reference standard for earthen plaster and wall systems. The International Residential Code does not yet include earthen construction in its base provisions, but owner-builder exemptions in most states allow individuals to build their own residence without a licensed contractor, and earthen structures built under these exemptions have received permits in all 50 states when accompanied by appropriate engineering documentation. The practical entry point for most people is not a new house. It is a garden wall, an outdoor oven, a small shed, or an interior partition wall. Projects that operate either outside the permit system entirely or at the low complexity end of the permitting process. These applications allow you to develop the mixing and building skills that Cob requires before committing them to a load-bearing structure. The soil test is the starting point. You need to determine the clay content of the soil you are planning to use. The simplest field test is the jar test. Fill a quart jar 1/3 with soil. Add water to fill the jar. Shake vigorously and allow to settle for 24 hours. The material will settle in layers: sand at the bottom, silt above it, clay as the top layer, and organic material floating on the surface. A workable Cob soil typically contains between 15 and 30% clay by volume. If your soil shows less than 10%, you will need to source additional clay. If it shows more than 35%, you will need additional sharp sand. The mix test comes next. Prepare several small test batches with different clay to sand ratios, typically 1 to 1.5, 1 to 2, and 1 to 2.5 by volume. Add straw fiber at approximately 1 pound per cubic foot of mix and form each into a test brick, approximately 4 inches by 4 inches by 2 inches. Allow all test bricks to dry completely, which takes between 3 and 7 days depending on temperature and humidity. The correct mix ratio is the one that produces a test brick with no shrinkage cracking, a hard surface that does not powder when rubbed, and enough toughness to resist being broken by hand pressure. Once you have found that ratio, you have the specification for your mix. Wall construction proceeds in lifts, horizontal layers of 6 to 12 inches of height applied at a time, with each lift allowed to firm up sufficiently before the next is added to prevent slumping. The cob is formed by hand into roughly rounded masses placed onto the previous lift and consolidated by treading and working with the hands to merge each new addition into a continuous, seamless wall mass. The wall is formed and trimmed to the intended line and face as work progresses, using a sharp spade to cut the outer surface clean. The critical rules for cob longevity are 3. First, the foundation must lift the base of the cob wall at least 12 inches above the finished grade to prevent splash erosion. Stone, concrete, or fired brick are all appropriate foundation materials. Second, the roof must provide sufficient overhang, ideally 18 to 24 inches, to prevent rainwater from running down the face of the wall. Third, the exterior face of the wall must be finished with a breathable plaster, lime plaster being the traditional and still recommended finish coat that protects the clay surface from direct rain impingement while allowing water vapor to pass through. A cob wall sealed with an impermeable coating is a cob wall that cannot breathe and will eventually degrade. A cob wall maintained with breathable lime plaster will stand for centuries. The cost calculation for cob is almost impossible to express in conventional terms because the primary inputs are labor and soil, neither of which has a standard market price. A rule of thumb from recent owner-builder cob projects in the United States puts the material cost at between $3 and $8 per square foot of wall area for a finished cob wall, including the lime plaster finish coat and any purchased aggregate needed to correct a low clay soil. The equivalent cost for a conventional wood stud wall with cavity insulation, sheathing, vapor barrier, exterior cladding, and interior drywall is typically between $25 and $45 per square foot in materials alone, before labor. The thermal mass benefit is not free in winter climates if the building is poorly designed for solar gain. A high thermal mass wall stores heat effectively only if it is receiving heat from somewhere, solar gain, through south-facing glazing, internal heat from a wood stove, or sufficient occupancy to maintain an indoor temperature differential from the outdoor environment. In a cold climate with no solar design strategy, a thick cob wall that is cold all winter is a cold wall, and no amount of thermal mass storage capacity will change that. The combination that works is thermal mass plus passive solar design. South-facing glazing to collect solar heat during the day, thick cob walls to store it, and sufficient insulation on the north and east and west sides to reduce the rate at which it escapes overnight. Part 6. Thermal performance in numbers. To make this concrete, consider a simple comparison. A standard 8-inch hollow concrete masonry unit wall has a steady-state R value of approximately R1.9. Adding a 2-inch layer of rigid foam board insulation on the exterior brings it to approximately R11. This is a typical wall specification for a residential building in a moderate climate zone in the United States. A 24-inch cob wall has a steady-state R value of approximately R9.6 to R12, depending on mix density. On a steady-state basis, these walls are roughly comparable. Now apply a diurnal temperature swing, a realistic outdoor temperature that goes from 55 degrees at night to 85 degrees at midday. A 30-degree swing typical of summer in a continental climate. The thin, high R-value foam-insulated block wall responds relatively quickly to this swing. Its low thermal mass means it does not store much energy. Interior temperatures in a building with this wall type will track outdoor temperatures with a lag of a few hours and will require mechanical cooling to maintain comfort during peak afternoon heat. The 24-inch cob wall, with its thermal lag of 8 to 12 hours, experiences the peak indoor heat transfer from the afternoon sun at 10 p.m. to 2 a.m., when outdoor temperatures have already dropped 20 degrees and you are asleep. During the day, the wall is absorbing heat from the outside. At night, it is releasing heat to the now cooler exterior. The direction of heat flow is in your favor during the hours that matter most for occupant comfort, and the mechanical cooling load is reduced accordingly. Oak Ridge National Laboratory research on thermal mass in buildings, published through the Department of Energy, confirms that in climates with significant diurnal temperature swings, which includes most of the continental United States, most of Europe, and most of the inhabited world, high thermal mass construction can reduce cooling energy consumption by 25 to 50% compared to low mass, higher value construction of equivalent steady-state thermal resistance. The cob wall your great-great-grandmother lived inside was not just charming. It was thermally optimized for human comfort in a way that the stick-framed, foam-insulated, vapor barrier box you probably live in now is not. Closing. There is a word in the natural building literature for the phenomenon I have been describing: embodied wisdom. The accumulated result of 10,000 years of experimentation by people who had no government energy efficiency programs, no building science journals, and no mechanical heating or cooling systems. They learned what worked by living in it, by feeling the results in their own bodies through the winters and summers. And the answer they arrived at independently, on multiple continents, across 10 millennia, was the same. Thick walls made of the earth beneath their feet, reinforced with a straw from their fields. The R-value conversation misses the point entirely. Thermal mass is not an R-value. It is a time delay mechanism. And time delay is what converts an uncomfortable building into a comfortable one, in a climate with daily temperature swings. The building industry does not talk about thermal lag, because thermal lag cannot be packaged, shipped, and sold. The material that provides it is the ground you are standing on. I am not suggesting you demolish your house and replace it with cob. I am suggesting that the next garden wall, the next outdoor kitchen, the next small structure you build on your property, you consider doing it the way human beings have done it for 10,000 years. With the materials the earth provides for free, at a cost per square foot that the construction industry would prefer you never discover. The Devon farmhouse built in 1540 is still standing. The towers of Houben have been inhabited for 5 centuries. The Pueblo at Taos has housed families for 1,000 years. These are not monuments to poverty or lack of options. They are monuments to a material technology that was solved correctly the first time, and that the modern construction economy has made it financially inconvenient for you to use. Subsoil, straw, water. That is the formula. It costs what the ground costs. The walls it builds last longer than anything you can buy at a building supply store. And the knowledge of how to use it has been waiting in the earth beneath your feet for 10,000 years.